All right, we're moving on to chapter 13.2, which is mostly about the idea of projectile motion. It's really just an application of using vector valued functions in an actual application here. So it's kind of a physics thing. If you've taken some physics, you may have studied the kinematic equations and maybe even projectile motion, which is basically describing the path of an object that is fired into the air and comes back down to the ground. So that's a projectile. All right, so just to make it kind of interesting, here's going to be our problem we'll work on. Let's say somebody hits a golf ball with an initial velocity of 100 feet per second at an angle of 30 degrees from the horizontal. And so this golf ball is going to travel and eventually land. Now there's a 10-foot tree 250 feet away from where the golf ball was hit. So the question we want to know is this golf ball going to clear the tree, or is it going to run into the tree, right? Is it going to hit it? So a position vector, we were talking about in 13.1, can be derived in this way. So, and we're going to do like a general case, and then we'll use our actual numbers here. So we're going to remember with the position vector, you can break down your motion into the X motion of the ball and the Y motion, the Y position. So the X position of the ball is going to be, okay, as the golf ball is moving along this path, it's moving in both the X and the Y direction. So we're talking just about the X direction. And that's all about how much of this initial velocity is moving in the X direction. Okay, and if you think about this vector, this initial velocity vector being broken up into its horizontal and its vertical component, the horizontal part has to do, that's the adjacent side of this right triangle. So it's the cosine. It's V naught cosine of theta times t. The Y position of the ball is a function of two things, right? It's a function of its initial velocity in the Y direction. That's what causes the ball to go up. But what brings it back down is the effect of gravity, of course. So the Y position is V naught sine of theta t minus 1/2 gt squared. G is the acceleration of gravity, which depends on whether you're using feet or meters. In this case, we're using feet. So when I actually put in the numbers, gravity in feet is 32 feet per second squared. We encountered that in 21B as well in certain situations. Okay, so running the numbers here, our position vector is going to be 100 root 3 over 2. That's the cosine of 30 degrees times t. The sine of 30 degrees is 1/2. So our Y component of the position is just going to be 50t minus 16t squared. Okay, we learned in 13.1, once you have a position vector, you can derive a velocity vector, just taking the derivative. So in general, okay, let me go back up here. This will be your general position function for a projectile problem. Okay, so they'll all be different, just different initial velocities and different initial angles. Okay. So taking the derivative of your general position vector function, our general velocity vector function is going to be V naught times cosine of theta. So that's going to be constant. And for Y, V naught sine theta minus, if you take the derivative of 1/2 gt squared, you get just minus gt. So here's your general velocity vector function for a projectile. So running the numbers, we get this vector. So a natural question, besides whether the ball hits the tree, is what is the maximum height of the ball as it travels along its arc? And we did similar questions like this in 21A. The difference is in 21A, the projectiles were fired straight up. They weren't given any horizontal motion to them. So, but now we have vertical and horizontal motion as these projectiles are launched. So when the projectile is at its maximum height, the velocity in the y direction is going to be 0. It's still going to be moving in the x direction, but certainly not in the y direction. So what we would do now, in general, you would take v sub y and set that equal to 0. Solve for t. T is going to be v naught sine theta over g. With our specific problem, that's going to be 50 minus 32t equals 0. So we're going to get t is 50 over 32, a little over 1.5 seconds. Now, that of course is not a maximum height. This is a time. This is how long it takes the projectile to get to its maximum height. So how do I actually find the maximum height? Well, I plug it into my position vector, but specifically I'm looking for height. So I would be plugging it into just the y component, r sub y of my position. Now, okay, so in general, if you plug in for t, remember we solved for t, we had v naught sine theta over g. If you plug that in here and simplify it, we get a general formula for the maximum height of a projectile. We can call that y max. V naught sine theta squared, all divided by 2g. Working it with our numbers, we get about 38.8 feet as our maximum height. One thing that could be a little confusing, when we hear the term range in calculus, we're usually thinking of the y values, right? How high and how low a graph goes. For projectile problems, for range, we're talking about how far does it travel horizontally. If you've ever familiar like with missiles, like the range of a missile is not how high it goes, it's how far that will travel, okay, horizontally. So how do we answer this one? Well, when our projectile hits the ground, who's going to be 0 now? R sub y will be 0, right? The y component of your position will be 0. So if we solve, we're doing this in general here, solve our r sub y, set it equal to 0, you can factor out a t. So one option is t equals 0. Well, that was at the beginning, right? That was when the projectile was first launched. So that's not really the answer we're looking for. If you solve this part for t, you get 2 v naught sine theta over g. Now, if you want to figure out how far that corresponds to, you would plug that into the x component of your position. V naught cosine theta times t. And if you plug this in for t, you end up getting v naught squared 2 sine theta cosine theta divided by g. And it works out a little bit nicer if you recall that that's an identity. 2 sine theta cosine theta is actually equal to sine of 2 theta. So x max, the range of our projectile, the horizontal distance it will travel, is v naught squared times sine of 2 theta over g. Okay. Obviously, these formulas can be memorized. They could be derived. That's what I'm doing here. Using our numbers, looks like our maximum range is 269 feet. Now, an interesting thing about the range formula for a projectile is for most of the time, there's actually 2 angles that you could launch a projectile at and get the same range, right? So for example, if I fire a projectile at an angle of pi over 6, 30 degrees, which is what our example is, it would actually travel the same horizontal distance as if we fired our projectile at an angle of 60 degrees, pi over 3. Why is that true? Well, if you plug in pi over 6 into your range formula, you go 2 times pi over 6 gives you pi over 3. So the range of this projectile would involve the sine of pi over 3. Whereas if you launch it at an angle of pi over 3, you're going to end up doing sine of 2 pi over 3. And if you go back and review your trig, the sine of 2 pi over 3 is exactly the same as the sine of pi over 3. So you would get identical values for your range, assuming you launched it at the same velocity. Okay, and what's true about them? Obviously, they are complements, right? Pi over 6, pi over 3, 30 degrees, 60 degrees. So you would get the same range if you launched a projectile at 10 degrees or at 80 degrees. They would both travel the same distance. One, of course, would not go as high as the other, but they would both travel the same distance. Now, another implication of our range formula, if you want to hit a golf ball or hit a baseball, you want it to travel as far as possible, right? So what angle would you want to launch your projectile at? Well, using our range formula, the maximum value sine could ever be is 1. And what value of theta would you plug in to get this to be 1? You'd have to plug in 45 degrees, right? 2 times 45 is 90. And the sine of 90 is 1. 45 degrees, of course, is pi over 4. And that might be intuitive, right? You know, if you launch the projectile straight up, it isn't going to go anywhere. And if you launch it at 0, an angle of 0, it's not going to go anywhere. So it seems to make sense that right in between, at pi over 4, it would be the maximum range, and it is. Okay, finally, let's answer our question. Will that ball clear that 10-foot tree that was 250 feet away? We know the range was 269, so it will certainly travel farther, but we need to know if it's actually going to hit the tree before it lands or not. So one way to answer it is you could set 250, which is where the tree is located, equal to r sub x and solve for t. I got 2.89 seconds, and then figure out what the height of the golf ball would be at 2.89 seconds. So if you plug that into r sub y, I got 11 feet. Recall the height of the tree was 10 feet, so it looks like that ball is going to barely clear that 10-foot tree. Just by a foot. Okay. One other example on this, there's a lot of examples. This one's actually 13.2, number 15. It's an odd problem that involve something you've done before in probably 21b, which is integrating derivatives to find a position function. You may remember in 21b, they gave you an acceleration and you had to take the integral of that to find velocity, the integral of that to find position. Okay, so it's kind of the same problem, just in a vector format. So let's say we're given the second derivative of r, second derivative of position, which we know is acceleration, is negative 32k. We're also given that dr dt, which was the velocity vector, evaluated at 0 is 8I plus 8j. That's our initial velocity. And we're also told our initial position is 100k. And we want to find r of t ultimately. So we'll start this by integrating our acceleration, negative 32k. I'm going to use this notation now for our vectors instead of I, j, and k. So 0, 0, negative 32. Integrate that with respect to t. The integrals of 0, both of those zeros are both constants, right? Remember, the derivative of a constant is 0. So these could both potentially be constants. The integral of negative 32 is negative 32t plus another constant. We don't claim these constants are the same, right? So we can label them C1, C2, C3. Now to solve for those constants, we have to take our initial velocity, which was given to be 880, 8I plus 8j, and then no k. So if I plugged in 0 for t, there's nowhere to plug it in here, but there is here, and set that equal to 880, we can see that C1 is going to be 8, C2 is going to be 8, and because that comes out to be 0, C3 would be 0. So our velocity vector is 8, 8, negative 32t. Integrate one more time to find your position vector, and integrate this velocity vector, 8t plus c1, 8t plus c2, negative 16t squared plus a third constant. And then once again, plug in, IC is kind of short, initial conditions. Plug in your initial condition, which was given. The initial position was 0, 0, 100. So if you plug in 0 for all your t's and set that equal to 0, 0, 100, both C1 and C2 are 0, C3 comes out to be 100, and then you just take that and put it right back into your position vector. And that's our final answer. There it is, right there. All right.